So today's session is going to be about slightly esoteric topic, eventing at the API horizon. What we'll talk through today will be split into about 5 parts. First, we'll talk through a little bit of REST 101. Second, we'll talk through some popular eventing patterns and how they specifically relate to REST APIs. Third is going to be the meat of today's discussion, which is going to be how do you basically use API gateways and event streaming better together. The fourth sort of phase of this presentation is going to be about what are these new ubiquitous interfaces and why you should be thinking about both conventional REST APIs and these things together. Finally, if the demo gods shine, we will also have a quick 5-minute demo. But briefly to get started, this is about me. I'm based in Bangalore, India. My regular job is at Platformatory Labs, a company that I founded. We're largely in the space of distributed systems and Kafka consulting in particular. And I've been a contributor to Kafka over the years. Some of my other interests are up here. Feel free to talk to me after this event. I have a lot of varied interests. I would love to talk to you and catch up with you on any of yours as well. So, in today's discussion, right, we want to first talk about just conventional request response architectures, right? How people in general build applications today. So what you might see in practically any application is, you've got a client, you've got a server, and you would let's take the the very overused e-commerce example. Let's suppose a client wants to create an order, right? So how would that work? A client would initiate an RPC of some sort. There would be a create order, and there would be a response returned. Now, what do we see out here, right? This is largely a privileged transaction between the client and the server. And of course, there is temporal and other forms of strong coupling. But the most important aspect is that there is, immediate feedback loops, right? And that's what makes request response architectures very interesting and very simple to build and to reason about. In contrast, you have messaging-oriented architectures, right? Which would look like this. Sorry, I've got some of my transitions in a bad place. Yeah, but in the messaging edition of this architecture, it would largely look like this. You would have a queue of some sort where your call to create order or the order object itself would be enqueued, and the service that actually is responsible for creating or doing whatever is the required thing with the order would consume the order and do the thing that is required. But from a client caller standpoint, there is no immediate synchronous feedback loop out here. And the point about this is there is much less coupling, and therefore it allows these systems to scale separately and independently of each other. But at the same time, these systems are a little more difficult to reason about in terms of what is going wrong, what is going right, amongst other things. So the point about this whole, REST interfaces and synchronous interfaces, asynchronous interfaces 101 is that they're both good for slightly different purposes. Synchronous feedback is very intuitive, especially when you have humans involved in the loop. So suppose you have a UI somewhere and a customer who's actually placing an order somewhere. What you'd actually expect to see is did the order actually get created, right? So you expect to see a response. Especially when humans are involved in the loop, or when there are external systems, which are outside of the service boundary, or generally the context boundary of the applications that are interacting with each other, synchronous feedback is very helpful, and it makes systems, especially any systems that have control interfaces or query interfaces, simple and easy to build. On the other hand, when you have a number of different cooperating services that are, a part of a larger, stack of services, potentially distributed, each of which, have their own service boundaries and intend to scale separately, as we discussed, messaging interfaces are much, much easier. In fact, the best way to think about it, messaging is as a shared journal of some sort, where a number of different cooperative services would really write logs to say, I did this. And that would in turn set off a chain reaction on the other side, where another cooperating service would do X, Y, Z in exchange. And therefore, each service being autonomous on its own, playing its role, would basically constitute a loosely coupled system with messaging as the primary interfaces in between. So one of the things that we should also touch upon, since we already touched upon the more generalized version, which is just making a create order RPC, is in practice you actually see REST out there, right? So the RESTful edition of the RPC is using a standard HTTP verb, making a post call to the order endpoint, and the response returned is an order. So it is fundamentally similar to RPCs. In fact, many REST puritans would say many so-called RESTful APIs are in fact RPC style APIs. But at any rate, this talk is not about hate OS or about REST puritanship. It's mostly about how these messaging interfaces can work with each other in a complementary way. So the RESTful edition is simple. It uses standard HTTP verbs, make a call, and get a response. So one of the things to think about, which is also important for this discussion that we're having today, is why REST has been historically so effective and so well adopted. There are manifold reasons for it, but some of the reasons actually are well articulated, pretty well ahead of time as well, in Roy Fielding's original dissertation around REST, which is really these points, right? Low entry barrier, uses standard HTTP protocol, and maps HTTP verbs to CRUD operations. There is extensibility, distributed hypermedia, internet scale. Anarchic stability is very important. You don't actually have control over a number of different things. So therefore, being able to standardize a protocol with all of these considerations in mind, and attempting to make it completely stateless, which is the original philosophy of REST, but also combined with a lot of neat features that REST offers, such as HTTP caching, in fact, ability to do things like e-tags and optimistic concurrency. All of these things make REST extremely powerful and very well adopted. So therefore, REST is pretty much the standard, de facto way to build interfaces to services. So I think the point that we are getting at in this section of the talk is that in real life practical systems that we all work with day in and day out, we see a combination of both the approaches. My mental model, strictly from a domain-driven design standpoint, is that scalable sort of internal journals make for good coordinating microservices or processes, however you want to look at them. And therefore, that is a great way to think about, how do you pass and communicate information between services, or specifically between services that are isolated through bounded contexts. Second aspect is for providing interfaces to control surfaces and query surfaces, REST is potentially a much better model. So that brings us to the second leg of this talk, which is that in the act of building RESTful services or operating RESTful services, where inter-service communication still has a messaging layer attached to it. What does a typical sort of mix and match approach look like, right? And this is going to be, basically two major archetypes, which we will talk further about, but also two major concerns. The first approach that many of you might be used to is the database write-through approach, which is that you have typically a service which writes to a database, right? And the way you would want to have event streaming applications or messaging applications consume off of this is typically through a CDC-like approach, which is that make a database call, put an item into a database. The resulting event is basically a row-level change that is sourced from the write-ahead log of the database and sent into the messaging system. So the further downstream services would consume that message from this message bus, event bus, Kafka, anything that you would consider, and therefore the rest of the the messaging chain ensues. Very popular pattern. The second pattern there is much more explicit in nature rather than being implicit, which is the database write-aside approach. Database write-aside is very important, especially when you intend to have control on the event payloads, and specifically when you also want to achieve durable atomic writes between both a messaging system and a conventional database system that might actually be in the mix. So the way this works is pretty simple. You begin a database transaction, and you would write that event to a durable message broker like Kafka that supports acknowledgements. And then if both of these succeed, then the transaction is committed, or otherwise the transaction is rolled back. So the interesting part about this approach is that it truly harmonizes how you do messaging with controls, schema-level controls, what is the actual event specifically in the context of the domain, how the event is structured, and where it gets written to is not a change data capture implication, but actually an application concern. So these two concerns largely solve the problem of how do you look at harmonizing messaging and RESTful services in a conventional database-backed world. But there also spring up two other important considerations and concerns. First concern is usually what we spoke about is in the context of a single service, single database potentially. In real life, you have tens or hundreds or thousands of services involved. So when events occur in this domain, which may be coupled along with their database write, update counterparts, coordinating these events across service boundaries usually requires an external actor at play. And that is pretty much on the border of what you would call as orchestration, right? Second concern is, what if we did not want to have an external coordinator for coordinating multiple services that are generating multiple events in the context of some business process? Now, a self-coordinating mechanism where each service knows what exactly to respond to. For example, an order got created. You got a service in the fulfillment domain. instead of the fulfillment service being orchestrated by a third party, you would have the fulfillment service basically subscribing to a change stream of the order service and then doing what it must do on its own volition. Now that would constitute what is more choreography. So choreography basically depends on cooperating services rather, which have strong, durable shared journals of work and know how to actually share this work. And the boundary in which this work is shared is along the principle of strong responsibility. Each service must do what it must do within its service boundary, also, which is a context boundary in domain-driven design speak. So, one other concern that also comes out of this is about the debate about orchestration versus choreography. But the other interesting underpinning to this challenge is what do the events themselves look like? And you can model events ground up. That is more about how you build greenfield systems. But in many systems, whenever for example, you use CDC or messaging systems that you don't control, such as messages coming out of commercial off-the-shelf systems, you need anti-corruption layers. You need a lot of layers on top of this. Why I'm talking about this is that there are three typical archetypes that arise out of how events in general work, and that's very relevant to this discussion. We can broadly classify them into these three categories. So you have light events or thin events, which are just event notifications, right? For example, an order just got placed, right? So there's no more information. It is purely a notification for other services to be informed that this happened, right? So there are pros and cons with all these approaches, but the best part about light events is that they have a very low surface area for unit testing, and because they focus on brevity, there is a lot of complexity that is itself avoided. However, there are also problems with light events, in that often the complete information of what exactly happened. For example, if an order got placed, what kind of an order was it? What was the product line item? What was the inventory at the time? What price was it sold at? Where does it need to be shipped? Is information that still needs to be collected from some domain service, and therefore subscribers of thin events basically just know that something happened. They don't exactly know what happened. Now, to contrast that with fat events are typically modeled to be much more expansive and to be descriptive of exactly what occurred, right? So it's a little less about, this happened. Well, in fact, it is about what happened. But in addition, it is also about, following are the details of exactly what happened. This is the order. So in its most expansive variation, it could be the entire object graph of a particular resource that just got created or got changed, or some other event occurred on it in the domain. The third category, which is about delta events or change events, mostly conforms to, this is what it was and this is what it is now. These are the fields that changed. So why are these two concerns important, right? That's mainly because event weightage, or the punching category of the event, thick events, thin events, fat events, delta events, they usually have an implication at the level of what is the integration pattern that you use, and there are also implications in terms of latency, how many calls do you need to make, how is subscriber complexity itself modeled, amongst other things. So, but basically, to read through what we have out here, so event weightage matters because as we just discussed, weight of the event usually dictates the nature of the work that will have to be done by the subscriber. Does the subscriber who subscribes to a light event, does it need to do pretty much all the work of piecing together what exactly happened, what needs to be done about it? Or does it know exactly, what transpired through the event payload itself? That's the second part that we will come to. But the second concern is, what integration pattern works better? Would you prefer orchestration or choreography? Is somewhat subtly related to, is it a fat event or is it a thin event? So the nuance here is that change data capture, CDC, as it is conventionally done, is a row level change, and that is archetype, in terms of, its archetype mapping, that is usually a thin event or a delta event, right? This happened is more the nature of how something is typically through a CDC stream. As we already discussed, thin events are great because they are low on the surface area, and delta events will also tell you what exactly changed. Let's contrast this with thick events, or what happens with more RESTful transactions. In fact, when we spoke about REST is representational state transfer. So it's a mouthful, and I think there's quite a bit of nuance in the way REST is named, right? RESTful interactions are usually fat events. That's because REST as a protocol itself is designed to be stateless. So therefore, the entire payload is usually communicated between both the server and the client. And then, therefore, almost always by definition, it is a fat event. Now, if you were to basically carry that over to the eventing world, where if you wanted to emit change events that contain exactly what happened on the API surface, it would result in basically a fat event. In fact, fat events are also better known as, I don't know who invented the terminology, in the same spirit as REST, it is the event counterpart. It is event carried state transfer, right? So just as REST is to HTTP APIs, in the eventing world, event carried state transfer would be the right terminology for communicating exactly, how something changed on a resource level in the domain. So, what works better, right? Thin events or thick events, and that is a matter of debate. In this session, we intend to do a brief demo of some approaches that have worked for us previously. If we had to throw in a bit of an opinion out here, we usually find that thin events are somewhat less useful in most contexts. There are a couple of reasons, right? One of the reasons you would want to do eventing is to basically promote less coupling between systems. Now, if that is the case, you'd also not want to have too many network chatty calls to find out, we know that something changed, but you don't want 10 queries coming back to you asking exactly what changed through a REST interface or any other mechanism. You would usually want to make the event payload self-descriptive to the extent that it carries all the information necessary, rather than having to promote more temporal coupling where the system of record needs to continue to be up, right, in order to respond to those queries. The best way to do this event carried state transfer model is usually at an aggregate level in domain-driven design speak. And often, if your APIs are modeled well enough for your REST resource to map to an aggregate, it usually checks out even better. You can have almost a one-to-one correlation between how you're looking at your resources, how you're looking at changes, how you're looking at events on the REST side of your interfaces versus what events are actually being emitted out of it. So that brings us to the third part, if we were to look at this worldview, RESTful services, fat events, um, what if there is a more interesting way to kind of do this? And that's what this talk is in fact about. So all this 101, 201 build up is leading up to a potential solution, an interesting pattern to look at how to synthesize um, events directly at the API level. So, sorry about the funky transitions. Yeah, okay. So the one way we can explain how this would work, and we'll try and do a quick demo right after this. How are we doing on time? Yeah, okay. Is to look at common API gateways or API proxies. In fact, it's very common to have most APIs in any enterprise usually fronted by an API gateway or a proxy of some kind. These are very interesting, mainly for the reason that you can externalize all the cross-cutting concerns out of each service having to implement its own authentication, authorization, rate limiting, so on and so forth, to an external layer. Now, one of the concerns that could also be considered cross-cutting is to think about how do I emit change events each time somebody changes a user profile or an order or whatever. So that could result in unobtrusive eventing, right? Without having services make code changes in order to basically, emit events out of the service, which is always good. It is largely in the spirit of, a sort of functional core, a functional core and an imperative shell. I heard this terminology elsewhere. So the way this works is we hook into common API gateways and API proxies, which are usually programmable in nature. Typically, we would have a push being generated in the log phase. What that means is after a response has been sent out to the client, in most API proxies, starting from Nginx to anything else, you would have different request response phases. When a request is received, when a request is proxied upstream, when a response is received, when a response is actually sent back to the client. The point at which the response has actually been sent back to the client, you are no longer in the request path. So that is a great way to basically plug in some eventing bolt-ons, and you have the ability at that point to play with the full request response workload. So as a function of what happened, it could be a put or a patch on a user resource or an order resource or whatever. If you were to then generate an order updated or a user updated event of some kind, be able to transform it to the kind of payload shape that you would want, and then be able to fan it out, that would solve some interesting problems and basically be useful. So there are three things. First is being able to bolt this on to conventional REST services to synthesize events, right, without having events explicitly emitted. Second thing is no code changes required. An API ingress or an API gateway is itself sufficient infrastructure to generate something like this. And third, no database or CDC connectors involved. We love CDC, but with that being said, this can often be a simpler setup while providing, fat REST events in pretty much Debezium JSON style CDC events, which should even be, workable with, Kafka Connect SMTs if there are any Kafka Connect users out here. So there are a number of extended possibilities. I'll breeze through some of this. One possibility is enhanced fan out and multimodal consumption models to RESTful subscribers. What that means is if you have a slow API and you would want to accelerate that API without changing its behavior, one thing that you could do is basically send a response immediately, or say request received, right? Send about 209, whatever. or a 202, accept it. And then after that, whenever you have a response actually ready, you could basically do a callback through a webhook or other things. So those are interesting patterns that can actually help accelerate API performance without losing the benefits of still providing a synchronous facade. A second implication would be what is emerging as a very popular pattern, which is long-running promises or durable async await, or durable functions, however you want to look at it. In fact, the interesting thing is there are, in recent times, some new RPC standards emerging for very long-running workflows, RPCs that span, days to weeks to months. Most of these RPCs will fundamentally execute with an event-driven core, but still providing the same request-response semantics or the RPC semantics at the client level. So that is potentially the best of both worlds, where many sort of integration aspects can be, aggregated into their own microservices. It's still event-driven fundamentally, but executing, in more reasonable ways, which is more orchestration-like. This, in the same spirit of like database write-through and database write-aside, can actually be done in a couple of patterns. What we are actually going to demonstrate here is gateway write-through. The gateway receives and basically generates an event. Nothing else happens in between. But for many events that require transactional semantics, like what if my gateway worker crashes in between or whatever, you could also look at a write-aside pattern where each time the request is received or the proxied, you could basically do atomic, multi-topic writes or basically transactional writes through something like Kafka, and basically have stronger consistency just in case you don't want to lose whatever is happening on the REST side. Wow, the naming it's 1, 2, 2, 3, 4. Okay, off by 1. All right. So there are other possibilities. You could also model for optimistic concurrency. One of the less exploited features of REST is being able to do optimistic concurrency with e-tags, and that could also fit into this. Therefore, having a RESTful event store that is still backed by Kafka is another possibility. But more importantly, you could also look at just audit trails for all APIs. You're running hundreds of APIs in your organization. You want an auditable trail for every call that is made, every mutating call that is made, for instance, forensics in general. So that's what we'll demo today. This is something we call as Eventception. This is a light version, deployable at the edge. The way Eventception works, the demo is worth more than what I'm talking right now, so we'll try and constrain it into 5 minutes. It's built on Kafka streams, but also a number of other things. It has multiple roles. So this solution can actually aggregate API proxy logs on a push basis, but it can also process them. For example, look at, if you've created order number 33, and then if you've changed order number 33 and you've changed the quantity to, whatever else, this can also generate CDC, that is change events, based on the last known state of the resource. It can also play well with connectors, forwarding it to databases, forwarding it to HTTP syncs through webhooks, amongst other things. The larger implication is there are REST APIs which allow you command and control capabilities. But if you want to bolt on a streaming capability to REST APIs, that is, I want to subscribe to order changes, whatever, and that's not just through Kafka, but through an interface like this might be an interesting way to do it. So there is a stream table duality metaphor here as well. That's it. So we'll just do a very quick demo and then we'll open up for questions. Okay. So I don't know if any of you can read this stuff, but let me. So the control surface of Eventception is pretty simple. we have YAML configurations, which largely is syntactic sugar to configure Kafka Streams topologies. So what we're doing out here is we use a Kong gateway out here, to which we will send a bunch of traffic. All of that traffic actually lands up on some Kafka topics, right? Which is basically what we are subscribing to out here, API logs in general. How does that happen? It happens through a Kong plugin, which executes after the response has been sent out. I won't go into the details of that, but basically what we are doing out here is we're doing some filtering. We could do arbitrary filtering. We're not interested in all the data. We're only interested in data where the request path is orders and it's a mutating event of some sort. We can do a little bit of massaging of that event with a JSON ATA transform. Again, I'm not going into too much of the details. We're almost out of time. But we have ability to deal with things like DLQs, amongst other things. And that's pretty much it, right? So let's bring this setup up. I'll actually show you the script. So we just have a script that generates a bunch of random orders. And to each of those orders, we actually send some update events, right? Which is to just go update the quantity on the order, for example. So what we expect to see is a stream of Debezium style change events, which basically is all coming out straight out of the gateway. No order service was harmed in this process or changed in this process. We're going to just run these scripts. All right. So that's created a bunch of random orders. And we have a script to basically make some changes on each of those orders. Right? So that is that. And what we intend to do is basically, there you go. Yeah, we want to consume change events, right? So each time there is an insert, you have a before after image, which looks eerily like Debezium JSON messages. But yeah, I could do more, and we generate basically change events on the fly. So this could be broadcasted to other services or through webhooks, to any other mechanisms. But in summary, basically what we are seeing out here is how do you source events straight out of an API gateway, make this usable in the context of RESTful services, and thirdly have a way to basically do some lightweight processing of these events to wrangle it into the right shape and form and fan it out to the services that are interested in doing that. All of this without conventional CDC or using database CDC connectors of any type. And that's basically what Eventception Lite and this talk is about. You can actually try some of this out. All you have to do is go do a Docker pull. It's a single binary. It should work with any flavor of Kafka. Thanks, everybody.